All right, let's pull back the curtain on something that's running our digital lives pretty much all the time, completely behind the scenes. We're talking about how computers take absolute chaos and turn it into order. I mean, really think about that for a second. You've got thousands of photos on your phone. You type in beach, and bam, there they are. How in the world does it do that so fast? Well, it's not magic. It's actually a set of incredibly clever strategies for wrangling massive, and I mean massive amounts of data. And to pull this off, computers use this killer 1-2 punch. First up is sorting. That's the art of taking a total mess and making it perfectly neat. And once everything's in its right place, then comes searching, which lets the computer find exactly what it's looking for in an instant. So what is sorting? Well, it's pretty much exactly what it sounds like. Imagine your bookshelf is an absolute disaster zone. Books everywhere, no rhyme or reason. Sorting is just the process of taking all those books and putting them in a specific order, say alphabetically by the author's last name. It's all about creating a logical, predictable structure out of a jumble. Now here's where it gets really interesting. Just like people, computers have different philosophies for how to tackle a big job. You've got the iterative method, which is like one really methodical person going through that messy bookshelf, one single book at a time. Then you have the divide and conquer method. This is more like getting a whole team of librarians to split the giant pile of books, each sorting their own little stack and then combining them all back together perfectly at the end. So let's start with that first librarian, the one who does everything step by step. This is the iterative method, where you just chew away at the problem one little piece at a time. And a perfect example of this is an algorithm called bubble sort. It's kind of famous for being one of the easiest sorting methods to wrap your head around, which is why we're starting here. The logic is dead simple. It just plods through a list, looks at two items right next to each other, and if they're in the wrong order, it swaps them. And it just does that over and over and over again.
Okay, let's watch it work with this list of numbers. The algorithm starts right at the beginning. First up, 5 and 1. Is 5 greater than 1? Yep. So they're in the wrong order. It just swaps them. That's it. Step 1 done.
Now it just moves on to the next pair. It compares the 5 and the 4. Again, wrong order, so they get swapped. You can kind of see what's happening here, right? The bigger numbers are slowly starting to bubble up toward the end of the list. So it swaps the 5 and the 2. And then it gets to the 5 and the 8. Finally, those are in the right order, so no swap needed. And just like that, one full pass through the list is complete. Now the good news is the biggest number, 8, is in its final spot. But look at the rest of the list. It's still a mess. The algorithm now has to go back to the beginning and do this whole slow process all over again for the remaining numbers.
Okay, so that was the slow and steady work harder approach. But what about that work smarter idea? Let's bring in that team of librarians and look at the much more elegant and powerful strategy: divide and conquer.
This is a complete paradigm shift. It's a whole new way of thinking. Instead of trying to sort the entire list all at once, divide and conquer. Well, it divides it. First, it breaks the big problem down into smaller, much easier problems. Then it conquers those little problems. And finally, it cleverly combines all those little solved pieces back into one perfectly sorted list. This is the secret sauce behind absolute powerhouse algorithms like merge sort and quick sort. They don't just nudge items one by one. No way. They split the list in half, then split those halves in half, and keep going until they're left with tiny little lists that are super easy to sort. Then they merge them back together. It's just a fundamentally faster and more efficient way to get the job done. Okay, so we've gone to all this trouble to sort our data. Why? What's the point? Well, this is the point. This is the big payoff. It all comes down to the search. See, having that sorted list is what makes lightning-fast searching possible. If your list is a mess, you're stuck doing what's called a linear search. That's like trying to find a specific word in a novel by starting on page 1 and reading every single word. It's awful. But with a sorted list, you can use a binary search. That's like opening a dictionary right to the middle, checking if your word comes before or after that page, and instantly throwing away half the book. It's brilliant. And that's the core idea right there. Every single time you make a guess, you slice the remaining search area in half. It's this incredible process of elimination that gets you to the answer at unbelievable speed. So, we know that some of these methods feel smarter than others, but how much better are they, really? In computer science, you don't just go with a gut feeling. You keep score.
There's a scorecard to measure how good an algorithm actually is. And that scorecard is called time complexity, or you'll often hear it called Big O notation. Now, don't let the weird letters scare you. It's basically just a rating for how much slower an algorithm gets as the list gets bigger. A very slow one, like bubble sort, which is O of n squared, doesn't just get twice as slow when the list is twice as long, it gets 4 times slower. It gets out of hand really, really fast. But a super fast O of log n algorithm like binary search, it barely even notices when the list gets huge. And when you're dealing with billions of items, that is a complete game changer. So what are the big takeaways here? First, that upfront work of sorting your data pays off big time when it's time to find something. Second, the strategy you pick really, really matters. That divide and conquer approach almost always blows the simple step-by-step methods out of the water. And finally, that efficiency rating, that time complexity, is what separates the algorithms that literally power our modern world from the ones that are just, good for a lesson. So the next time your phone finds that one photo in a split second, or your music app instantly pulls up a song, you'll know a little bit more about the elegant, invisible logic that's making it all happen. Which really just leaves you with one question to think about. What other invisible algorithms are out there, quietly shaping your digital world every single day?